Hi everyone, my name is Natalia. Thank you for joining our webinar on how to solve fraud with deep learning and graph embedding. I want to let you know that you will receive the recording of this webinar within 24 hours, and also that our team has joined the chat. So feel free to send all your questions. We'll do our best to answer. You will be able to find the chat box on the left side. And now I'll pass along to Jim and David, who are the panelists and presenters for tonight.
Hi, my name is Jim Dowling. I'm the CEO of Logical Clocks, and I'll be joined on this webinar by David Jalava, who's the head of data science at Logical Clocks. And who are Logical Clocks? Well, we're the makers of a platform called Hopsworks. It's an open source data intensive AI platform for developing and operating models at scale. And it also includes the world's first enterprise feature store for ML. So let's get cracking straight away. We're going to talk about fraud, and in particular I'm going to talk more about money laundering, so as a specific type of fraud than the more general case of fraud in the case of finance. So money laundering specifically involves turning dirty money, so money acquired illegally, into clean money, typically through a sequence of banking transfers. So you're going to transfer money from one account to another. The money starts off as dirty in the system. By the time it comes out as clean, we should be able to use that money to buy things. So the three phases of money laundering involve placing that money or smurfing it into the network, spreading that money out, and then integrating it. So there will be patterns that the fraudsters develop over time to place the money, to spread it out, and how to integrate it. And the typical game that is played out is that the anti-money laundering authorities try to identify the fraud schemes, and the fraudsters try to come up with new original schemes or patterns of money transfer that will enable them to get around the existing techniques for identifying anti-money laundering. Now we have a little visualization here which shows you a graph, and on the nodes we have the users, and the edges, the lines between the nodes, are the transactions, so the transferring of money. So what this basic graph shows you is typical patterns of money transfer between customers, for example, in a bank. And we can see one or two nodes have a lot of incoming edges, with the size of the node maybe giving reflective of how much money that node has in its balance, for example. You can have different, of course, properties for nodes, not just balance of accounts. But what we can see here is that visually we may be able to identify patterns in the data that the rule-based approaches that are currently the state of the art for money laundering, or the current de facto platform that people use to identify money laundering, and will not be able to capture some of these patterns that you can even see with the naked eye. So typically investigators in money laundering will also use visual tools to try and inspect the transfers of money to help them identify if fraud is occurring or not. I'm going to get back to that later on, because we're going to talk about feature engineering and these graphs and what we call graph embeddings. But before that, I'm just going to move on to talk about why we as a company, Logical Clocks, we build a horizontal platform for deep learning, machine learning, and the feature store. Why are we talking about anti-money laundering? Well, we have experience in this space. We've worked with a customer to develop GANs, generative adversarial networks, to train models with 40 terabytes of transaction data. We've used Spark for feature engineering to compute these graph embeddings. That's a very important feature for money laundering. And we've also used TensorFlow and GPUs, many GPUs on our platform, to train these GANs to classify transactions as money laundering or not money laundering. And we've used the platform as a whole to manage this data, the features for our models, to scale out the training, to store the data, and to store the models, and to serve them. So there's a reference white paper that you can read up on here if you want to find out more about that particular use case. But I'm going to move on and talk about the general problem of existing approaches, the rule-based approach for anti-money laundering versus the deep learning approach to anti-money laundering. So I mentioned the rules-based approach, but effectively the existing systems for identifying money laundering in transactions involves taking attributes of the transactions and also some state that you have stored about the users, the customers, the banks, and so on, to alert if a given transaction matches a rule that you've defined in effectively a list of rules. You may have hundreds or thousands of rules potentially, and if any of them matches, you're going to alert an investigator, and the investigator will then manually see if this and determine and make a judgment if this particular transaction involved fraud or not. So the fraudsters obviously try to infer some of these rules. Some simple ones are if the amount of money above a certain threshold, the amount of money being transferred is above a certain threshold, well then we might want to investigate that, and they obviously then ensure that the amount of money transferred is below those thresholds that are in the rules. Now, the way in which we would approach identifying transactions being fraud using deep learning is that we're going to train something called a model, and the model will take data. It's going to take what we call training data, and the training data will be basically a set of transactions, and those transactions will have labels for them saying whether this transaction was a good transaction or whether it was a bad transaction. And when we've trained the model with deep learning, we're going to use GPUs to train the model. We can use that model in a different system. So in the actual online application, we can take in the amount of money being transferred, the customers involved, and all of the features that we used when training the model. So typical features that you use will be these graph embeddings, but also temporal features like the number of transactions that the customer has executed in the last hour. And if the model predicts that this particular transaction was potentially fraudulent, an alert will get sent out. Now, one of the topical issues related to using deep learning and AI for anti-money laundering is, what does the regulator think? And it depends, of course, on the jurisdiction. But regulators typically say yes to the rules-based approach because they're used widely around the world. And for the money laundering approaches using deep learning, they're asking questions saying, well, let's have a look. Let's see what evidence you can bring to me about whether this approach is robust, about whether it's trustworthy, and whether we can explain the predictions that have been made. Now, currently, that doesn't mean even if you can't put your deep learning AML system into production today because the regulator won't allow you to do it, it doesn't mean it won't add huge value, because if you have an AML-based approach using deep learning that can better help the investigators, so we have this person over here who's going to investigate the transactions, and this becomes another piece of information that they get to help decide on whether a transaction is fraudulent or not. For example, to sort, when you have many different alerts to process, you might use the deep learning approach to identify those which are of the highest priority. But also, very importantly, this deep learning approach may generate more alerts so that you won't miss any fraudulent transactions that maybe the rule-based approach would have missed. So, if you want to deploy an AML-based approach with deep learning in production, you have to go through a number of steps. And these models are actually quite complex to put into production because they're operational models. What that means is they're running 24/7. You have your application that's taking in the transactions, and it needs to then look up the features that are going to be used to make the predictions. So you'll have the transaction data itself, but you'll have many more features that were used to train your models on. So the number of transactions in the last hour, these graph embeddings that we talked about. And this is quite an advanced type of machine learning system that you're putting into production. Simpler models that you might want to try out with AI would be, hey, I have a bunch of customer records here, and I'd like to train a model and predict which is a high-value customer, so segmentation. Or maybe I can automate that process, and every time we get updates on customer accounts, we'll segment them automatically. You can also use batch applications that make predictions that intelligent applications can read up. So when you log into your web page, it'll give you recommendations about what to do. But these were computed offline using analytical models. Operational models require infrastructure support to serve the features with low latency to the model so that they can make their predictions within the latency budget they have available. Now, if we think about the AML problem as a supervised machine learning problem, which is what deep learning is traditionally about, you'll see that one big problem jumps out directly, and that is what we call imbalance. We have massive imbalance between the number of clean transactions. You can have billions of clean transactions and only thousands of dirty transactions. And typically the approach in supervised machine learning is to downsample the larger class, the clean transactions, and upsample the dirty transaction class. But the difference is so large here that this becomes impractical. So we have to have a different approach. That's not going to work straight out of the box. So what do we do? Well, before we look at the approach which is based on anomaly detection, we need to identify how we're going to evaluate this particular models that we train. And typically we would model them based on something called an F1 score. It's quite typical in machine learning. You'll say, well, we'll calculate the precision, recall, fallout for our model, and we'll weight them all equally. But you don't want to weight the decisions of a binary classifier for transactions as fraud or not equally. So if, for example, you have a good prediction, that's fine. If you have a good prediction that says it's not a money laundering transaction, that's fine. There's no problem there. It's when you have a false positive, so you think that a transaction is dirty, but it's not. The result is that it's not. Then you have work and cost, and that's pretty bad. You know, large banks typically will have hundreds of people who investigate these alerts, and it's a cost that a company has to bear. But the worst case is that if you predict that a transaction is clean, but in fact it wasn't, it was money laundering, you can have very large fines or even jail. So this is a significant problem if you have false negatives in the predictions made by your binary classifier. So you want to take that into account when you evaluate or the performance of the models that you're going to train. So let's look at this approach we're going to look at. It's basically anomaly detection. Anomaly detection is typically unsupervised machine learning. Unsupervised machine learning often uses k-means clustering for unsupervised learning, or PCA. And the problem with these approaches, they don't scale. So they don't scale with available compute or available data, whereas deep learning does. So we do have some labeled data available to us, so we're going to call this approach semi-supervised machine learning, not fully unsupervised. It's a class of machine learning where we have a small amount, we have an amount of unlabeled data, and we have a large amount of labeled data. So let's look at the kind of approaches you can use in deep learning for doing anomaly detection. You can use variational autoencoders, which are quite widely used, and they're easy to train, but unfortunately their performance is not the state of the art. We're going to talk a bit more about generative adversarial networks, or GANs for short. And what GANs do is that they'll learn the input distribution, in our case, of the transactions. So we'll have many features to describe these transactions, and the GAN will learn a manifold of the normal samples. One question you might have at this stage is, well, what happens if the training data I have has many cases of fraud, but the training data says that they're not fraud? So if I have what I call pollution in my data set. Well, you can read this link to find out more details, but a small amount of that fraud should be okay. A small amount of pollution in your data set should be okay, is the bottom line. Now, there's been a lot of research in this field of using GANs for anomaly detection, and we have some links here: BiGANs, big GANs, big BiGANs, GANOMALYs, FANOGAN, and GANs for fraud. But I'm going to go through the basic first step, describing what a GAN is and how it's been used originally, and then we'll move on to the approach that we used based on adding an encoder to this typical GAN network. So the classic approach would be to basically say, hey, let's use a GAN discriminator to do the anomaly detection, and I'll show you what that means. So firstly, the GAN will have our large amount of training data of the good transactions, and we're going to train a convolutional neural network. We'll call that the discriminator to basically predict. We have these as labeled, and these are good transactions. So we're going to train this discriminator, a convolutional neural network, and it will be able to say, well, these transactions are good transactions, and other transactions will be bad transactions that don't come from the same data distribution of the good transactions. What the GAN itself will do is it will generate random vectors to begin with and pass them through a generator, and the generator will generate sample transactions. It will contain random data to begin with, and it will ask the discriminator, is this a valid transaction or not? And the discriminator will say, nope, it's a bad transaction. It'll generate a loss, and then we'll update the weights in the generator to reflect that. So over time, what should happen is that this generator should be able to generate sample transactions that actually can be classified as good. Now, by the time that happens, the discriminator will have learnt enough about the original data distribution of our good transactions to basically say, well, a lot of these bad transactions weren't good transactions. I can pretty well classify transactions as either good or bad. So what you can do at the end is you can basically just pull off the generator. You're left with this convolutional neural network, a discriminator. It's a binary classifier, and you can feed your new transactions in here, and then the discriminator will tell you if they're good or bad. And that's a discriminator-based anomaly detection GAN. Now, that particular approach is problematic because you're prone to what's called mode collapse. So the transaction data that we have in money laundering typically will not come from one single distribution but be multimodal. You may have different ways in which money is transferred between people. You'll have different patterns of transfer. And because we have these multiple modalities, the GANs often can reach what's called a Nash equilibrium. That's when they finish training. And they'll reach this Nash equilibrium too soon, and they won't have learned all the different modes. So we call that mode collapse. We've only learned some of the modes. GANs are also highly sensitive to the hyperparameters that you use. And there's a great link here called GAN hacks to give you some tricks on how to make these GANs, how to train the GANs and how to make them converge, and how to find good hyperparameters. We're going to talk a little bit later about the MAGGY platform we have in Hopsworks to enable you to do parallel hyperparameter tuning, which enables you to massively reduce the time it takes to find good hyperparameters. So how do we address the mode collapse problem? That's a hard problem. One way is if you have prior knowledge, you can use multiple generators, and you can say, well, I know the different modes of distribution of this data. I can just have generators for each one. So that's quite challenging because we don't always know these different distributions or the different modes in the distribution. So FANOGAN was proposed as a technique which replaced our deep convolutional GAN with a Wasserstein GAN with gradient penalty. And what it did was it added something called an encoder to the network. And the encoder was trained after you trained the GAN. And Berg from Linköping and colleagues improved this architecture by training the encoder and the generator in parallel. So I'll look briefly at that particular architecture because that's the one that we've been working with. So what this is the same as the previous generator and discriminators. This is our generator, this is our discriminator. Same architecture as before. We have our good transactions here, and then we have our random vectors at the beginning are going to be fed into the generator, and these will be created as the transactions that we want to send to the discriminator to classify them. And then we get a loss computed. So what's different from this is that firstly the Wasserstein loss is a distance rather than a yes or no, so that helps in training. But the second point is that this output of the generator we feed into the encoder. And as you'll know, in variational autoencoders, the generator will generate this representation G of Z from the input. So this is G of Z here, which comes from the input Z. And the encoder will just try to recreate Z. So it's going to try and, over time, it will learn to recreate the input vector Z as Z hat. So when the system is converged and it's well able to recreate the input, and the generator is able to fool the discriminator, what we'll have is a trained network. And this trained network, we don't need the discriminator anymore. What we're going to do is we're going to feed in our transaction as Q. So this is going to be our transaction that we want to classify as anomalous or not anomalous. And we feed it into our encoder. It generates Z hat or Z hat, and then we feed Z hat through the generator, and we get out G of Z hat. So the difference between these two, so the vector that came out, the output of the generator, sorry, G of Z hat, and then the input Q, that's going to be how we define our anomaly. So we'll have a function called A, which takes those two inputs, and it will return back the difference or the level of anomality of this particular transaction. So at that point, this is the basics on anomaly detection, and the question is, well, will this work? Will this help me improve my predictions of whether transactions are anomalous or not, or fraudulent or not? We have two evidence points here for you. One is in China, 2 commercial banks helped reduce losses by 10 million renminbi by using GANS. And another one is Swedbank, who presented a talk at the Spark Summit last year, and they presented this as their conclusion that we can see here. The GAN-based approach is the same for the number of true positives, so it's not missing fraudulent transactions, but it generates far less false positives. So it's not telling you that there's lots of transactions that have alerts but actually shouldn't have alerts. So that reduces the cost of processing all of these alerts that get generated by the rule-based systems. So let's move on to Hopsworks and show how we can develop a GAN-based approach for money laundering on our platform. So firstly, I'll start by describing how the platform fits into existing infrastructure that many organizations already have in place. Typically, the data that you would have for transaction data and know your customer data will be in a data warehouse or a data lake, and you'll have existing BI platforms for analyzing that data, and you have data pipelines pulling data from back-end platforms over here. So what Hopsworks basically does is it allows you to build feature pipelines that can be run on our platform or on an external platform if you want. They can be written in Python or in Spark or PYSPARK, and they'll feed the features into the feature store, and the feature store then makes those features available to the online AML applications that can pull the features with low latency. So the historical features like these graph embeddings and temporal features like number of transactions users have performed in recent amount of time, they'll be pulled from the feature store in real time. Data scientists will use the feature store to train models, so to select features that they want to use to train a model for money laundering. And analytical models can also use the feature store to read out features and then score them in batch applications. So Hopsworks itself is a platform that has this key built-in feature store, but we can also run TensorFlow, scikit-learn, PyTorch applications as distributed applications. We have support for managing Python dependencies in Conda. You can run Jupyter notebooks in pipelines. And then there's support for TensorBoard, which is useful when you're doing deep learning and debugging your applications. For feature engineering, you can use Spark or Flink, for example, and it can be batch or streaming applications. And you can either plug in an external Kafka or use one that comes with the platform. We support orchestration either in Airflow internally in the platform or in an external Airflow cluster. And then the data, the features are all stored in our file system, HopSFS. And if you're running on S3 or Azure, it'll plug into either S3 on AWS or Azure Blob Storage. Serving models can be done on Kubernetes clusters, and we also support monitoring of those models. So if you serve those models through Hopsworks, we'll store the predictions in Kafka, and then you can monitor those models by having, for example, a streaming app or just a normal batch app that runs at periodic intervals, reading the predictions, computing the data distributions on the traffic in those predictions, and comparing it with the features in the distribution of those features in the feature store. So you're looking for drift between the live traffic features and then the features in the feature store. Now this platform can be run on-premise, it can be run in any cloud, but if you run it in for example, Amazon, you can run the cluster with an IAM role. So that's an IAM profile. You can hook it up to your Active Directory cluster for single sign-on, and you can hook it up also to Databricks, SageMaker, Kubeflow, or EMR to do your feature engineering and model training. And internally in the platform, we have a project-based multi-tenancy security model for managing, for example, development, staging, and production projects and feature stores. And you can run jobs internally in the platform or on external services. So how do we manage the features then? And this is a key point. So when we want to productionize this anti-money laundering application, some features will have very low latency. So the features that arrive with the transaction, the customer IDs, they will have low latency. They'll need to be transformed within milliseconds into features that will be fed to the prediction engine, the model. But we'll also have features that reside on maybe Kafka servers, on operational databases, data warehouses, and also on data lakes. So the feature store is a way of integrating these together, taking these features and pushing them to this central location where your online application, the anti-money laundering application, can retrieve the historic features with very low latency. So it's going to look up the number of transaction counts users have done, the feature embeddings, and so on. But the data scientists can also use the same feature store to generate their training data. And you will have different feature pipelines that run at different intervals, so different cadences. Maybe they'll run every day for KYC, know your customer data, every hour for your user profile data, and even lower latencies for other types of features. So the problem here is that both the online application needs very low latency access, and the training data might need terabytes, tens of terabytes of data. So there's no single database that provides those capabilities. And like all feature stores that are out there today, we have two databases, one for the low latency access, and we use MySQL Cluster for this. And MySQL Cluster is an in-memory database based on the NDB engine, so it's not InnoDB. And then we have Hive as the offline feature store. So Apache Hive is our offline feature store. So one of the challenges as an engineer is to write these feature pipelines to write to both of the online and offline feature stores. That could be quite difficult, but we provide a data frame API where you can just push this data frame to the platform, and we handle the complexity of making sure those features end up in both the online and offline feature store if you so wish. You may only wish them to be in online or offline. So when the features are in the online feature store and we want to productionize our anti-money laundering application, firstly we have infrastructure that's highly available. So our online feature store can be made redundant or replicated across, in this case, availability zones in AWS. And models can also be deployed redundantly, for example, in Kubernetes across availability zones. So the online application, when our transaction arrives, we'll have only a small number of features in the transaction, things like the customer ID, and customer IDs involve the bank IDs and so on. So what we'll need to do is contact the online feature store and get the features that aren't available in the online application. This means basically building the feature vector, ensuring the order of features is correct as well. So once we have that feature vector, we can then send that feature vector to the model to make a prediction. And as I mentioned before, typically your model will be served over the network rather than be embedded in the application, because if you separate the life cycle of the model and the application, then they can both be updated independently. Now, how do you develop these applications? Well, we typically see that users want to start on their notebooks in Python, and then when they need large amounts of GPUs and compute, they go to a cluster, and then they run, in our case, they'll run the same notebook, the Python notebook, in a PYSPARK job. So we provide specific support for making the same code run across all these steps. But I'll just introduce the life cycle as we see it. So as we see it, we have a feature store at the beginning where our features reside, and the data scientists will use the feature store to create training data and perform parallel hyperparameter optimization studies. So if you have 100 GPUs, you should be able to find your hyperparameters 100 times faster, and if you have 100 GPUs for training, you should be able to train your models 100 times faster. And then model serving is done on Kubernetes, which enables elastic serving of models. But one of the challenges here in moving through these stages is that frameworks require you to rewrite your code. If you're using TensorFlow, rewriting your code for distributed training is typically what you need to do. And for hyperparameter tuning, you might rewrite it, and in your notebook you've rewritten it. And it's very hard then to move iteratively forwards and backwards through these phases. So what we have is a framework called MAGGY that enables you to do this. It's open source. It was presented at the Spark Summit in June, and you can read up more on this blog below about it. But effectively what you do is write one training function. We call it an oblivious training function, and it can be plugged into all these different phases. And if you're curious about how that works internally, it's a Python library, and if you're running it in the cluster, it will use PySpark to to distribute all of these tasks, these asynchronous trials, to the different workers in your cluster. So the optimizer runs in the driver in Spark. Now, Hopsworks itself is available as an open source platform, and you can do pretty much anything in the platform except connect it to things like Kubernetes, Active Directory, and GitHub. If you want to do that, you need to use the enterprise version or the managed SaaS version of Hopsworks called Hopsworks.ai. It's available at Hopsworks.ai. You can go ahead and register for an account there. It's free to use until the end of September at the moment. It's currently available in AWS and will be on Azure within the next few weeks. So at this point, I'm going to actually hand over to David, and what David is going to do is walk through an example of how we can simulate an anti-money laundering data set. This is based on a Kaggle data set that's public out there. The source code for his demo is available at GitHub at the URL shown here. And what he'll do is we'll look through some of the features that you might want to generate from a data set like the PaySim AML data set. So things like graph-based features, where we want to capture a lot of the graph-based information into a graph vector. Frequency features where a graph embedding, I should say. So frequency features where we learn how frequently an account is used. Account features where we look at the magnitude of the amount of transactions. And then time since features and velocity change features where we look at changes in the behavior of accounts and the speed of transactions. So with this, I'll hand over to David, and he'll walk through a notebook and example running on the Hopsworks platform.
Thank you, Jim, and thank you everyone for attending this webinar. So I'm going to demo how to use Hopsworks to develop deep anomaly detection model and how to use this model to detect fraud in banking. For this demo, we are going to use PaySim dataset, which is from Kaggle, and it's a simulation of financial transactional data and contains variables such as amount transacted, type of transaction, also balance before and after the transaction, and it also contains labels whether this was marked as a fraudulent or if it's a valid transaction. If we look at the data set to what's the difference between fraudulent and the valid transactions, we will discover that fraudsters use the transfer and the cash out, and balance reveals that they mainly targeted the customers that had a high volume of deposit, and after the transaction they immediately cashed out. If we look at the next month's data set, for example, we can see that they employ a different scheme. So instead of immediately cashing out, they started to gradually take money out and also used another type of transactions such as a payment and a debit card. However, behavior of valid transactions stayed the same. So when we want to detect something anomalous, something that deviates from the rest of the data, the very effective way is to learn what is a normal behavior, because fraudsters will develop new schemes every time, and the effective model is if we know what is normal distribution, what the distribution of the valid transactions, and be able to detect something that has either never seen before or it deviates from the rest of the normal or transactions that has never been reported as fraudulent. This type of models, as a semi-supervised or unsupervised learning, GAN-based anomaly detection models has been proven to be very, very effective. For this demo, we will now compute the graph features or the graph embeddings. Then can be later used to the downstream analysis and fed to the anomaly detection model to produce to classify whether transaction was fraudulent or valid. For a feature engineering, I'm in this notebook I'm using Spark to compute features, transaction features, and then node features, and I'm using Hopsworks feature group or Hopsworks feature store API to register these features as a feature groups. In this case, I'm registering in transaction features and asking Hopsworks to compute the statistics for features in this feature group, and I also want to version this feature group. So in case next time I'm going to compute or add a new feature or use a different way to compute these features, I will attach a new version, and this can be later maybe used for creating a new version of the training data set that can be used for a new version of a model. The similar is done for node features. This is how Hopsworks feature store the UI looks like. Here is feature groups or transaction feature group which we computed. We can look at the statistics. What is the descriptive statistics of features? What's the correlation between features and whether they are any clusterings or not within this feature group. Here we can see whether this is an offline or on an online feature group. We have not enabled here online features, but we will need the online feature groups if we are using these features to do if you are doing a real-time scoring. For example, if you are monitoring transactions in near real time. Offline features is usually used for offline scoring or batch scoring, or creating training data sets for the model training. I'm also here since in the next notebook I want to use stellar graph, and I want to use as a pandas data frame to create edges from transactions and the nodes and their corresponding features to construct the nodes for the graph. I'm saving the transaction features and the node features as a CSV data set that later can be used to read in a pandas. And similar here, I'm also versioning a training data set in case I will use a new version of the feature groups to create this training data. I will attach the new, or I will it will have a new version, and this new version of the training data may be used to create new version of model. Since now we have training dataset can be found in a training dataset tabs, and similar to the feature episodes, we have a descriptive statistics and also schema, and whether we have a split of for validation and training, etc. In this case, we created one training dataset. So next step, I want to compute graph embeddings, and I am going to use a stellar graph and word2vec. But to compute embeddings, first we need to decide a couple of hyperparameters. For example, how many random walks we want the algorithm to make, how many hops should be made from each node, and what is the size of the embeddings we want to compute. So Hopsworks comes with library MAGGY. In MAGGY, you will design the hyperparameter search space, and you will ask MAGGY to find a best combination of these parameters based on the metrics you will ask. In this case, we asked to give us a best hyperparameter combination that gives a maximum binary accuracy. So we are going the direction. We will maximize the direction. We can specify a number of trials, and if you are doing if you have a multiple GPUs, then we can do a multiple hyperparameters in parallel. So MAGGY will then report back us the best hyperparameter combination, and it will also register in the experiments module, and this is how the experiments module UI looks like. Here we have experiments we conducted. It will have all the metadata attached, plus we will have a directory where all these experiments are saved, and we also have a Conda environment in case we want to reproduce this experiment. Now, because we have now already a best hyperparameters for computing embeddings, now we start to do a embedding computation on an entire data set, and we will use the best hyperparameters reported. And since we know that this is now the best hyperparameter and best model we have, I'm going to register a feature embeddings features as embeddings feature groups in feature store. Here we have it, embeddings features here, and we also, since we are going also to use this as an input to our anomaly detection model, I have saved a embeddings features as a TF records file format, embeddings training data set as a TF records file format. Now, Hopsworks supports different file formats. Previously, we saved it in a CSV file format because we wanted to read it as a pandas. Now we want to read it as a TensorFlow, so we saved it as a TF records file format. And here, similar to feature groups, we can have a new different version of this training data set, and we will have also either we save the different splits, or we can find a schema which will be very useful if we want to parse, especially if we are using TF records dataset. Now we have everything we want to start the training to our anomaly detection model, but similar to the embeddings, we need to decide hyperparameters. As we mentioned earlier, to do a anomaly detection on a semi-supervised or unsupervised manner, GANs are proven to be very effective. However, GANs are notorious to be hard to train. So they are very sensitive to hyperparameters, and you will have a much higher or a much larger search space. Like you will need a hyperparameter for your discriminator model. You will need a hyperparameter for a generator model. And if you have a generator-based anomaly detection model, and if you have another encoder to measure distance, then you will have you need a hyperparameter for the encoder model as well. So in this case, it's really important to have a good hyperparameter or hyperparameter optimizer, and also to be able to decide to give a yearly stopping. So in case some combination of hyperparameters is not performing well, then it's a good idea to do a yearly stopping, which MAGGY allows, and move to the new hyperparameters, so we don't waste our resources. And if you have multiple GPUs, Hopsworks and MAGGY can scale this to do multiple hyperparameter experiments. Now, similar to the previous, this will also report us the best hyperparameters and register in the experiments UI, and then this can be used to train our classifier. and we will use reported hyperparameters. To mention here, Hopsworks supports to do using multiple GPUs to do a distributed training, and Hopsworks also supports to do a distributed training on multiple workers. So you can potentially scale your distributed training on hundreds of GPUs. Now, since again we know that this was the best hyperparameters we had, at least for this version of dataset, I'm going to export a model and register to the Hopsworks model registry. And every time I retrain it or want to export to the Hopsworks model registry a new model, Hopsworks will version it and report us the metrics we used for this model training for this model. And later we can use this to pull a best model if we want to deploy for a serving. This is an example of the REST API. Here I'm asking which model I want. I'm asking to give me a version of the best model and what's the metric of this best model. I am spinning up Hopsworks models serving server, TensorFlow server. Here, if we can see that the model server is up and running, and we can send predictions. So if we send the vector that was used for a training, and then it will send us back a score for this particular vector, so we can identify whether this graph embedding belongs to the fraudulent or a normal transaction. Now this is a short overview of the Hopsworks and how can you use to develop deep anomaly detection model and how to manage the entire life cycle. But I want to mention that in the fraud detection in banking, it's important the models have a explainability, and the rule-based systems are very good to explain, very easy to explain why or why not this transaction was classified as valid or not valid. However, they are also notorious to produce a large number of false positives. Usually they produce hundreds of thousands false alerts, and usually 1 or 2% of these alerts are reported to the law enforcement, so-called true positives. This type of models can be used to identify or to help investigative teams which of these reported alerts can be prioritized. For example, if both systems reported the transaction is fraudulent, then the investigative teams can use it to prioritize which of these alerts produced by the rule-based system can be prioritized. It can also help in case something new anomalous or a new scheme can be discovered. Then this can be later used also to develop a new rule or to identify a new scheme as early as possible. Thank you very much, and if you have any questions, we'll be very happy to answer.
Thank you, David, Jim, and everyone who stayed with us to the end. Once again, you will receive the video and the slides of the presentation by email, but if you want to stay up to date on everything that we're organizing, or if you want to contact us, go to our website at logicalclocks.com, or you can email us at marketing@logicalclocks.com. That's it for tonight. Thank you, and have a good day or a good evening depending where you are.